Hello all and welcome to the Hijacking Network Elements and New Type of Attack webinar. My name is Mert Duran. I'm the Product Marketing Manager for Simsoft and I'll be moderating this session. In today's webinar, Fredrik Söderlund will be discussing his research into a new type of attack on SS7 networks, which I think is very interesting as well as worrying. The findings that will be discussed today have already been passed on to the GSMA Fraud and Security Group, and Fredrik has presented his research at last month's Troopers Security Conference, but this is the first time that we're sharing it with a wider audience, so this is all very new. Just to give you a little background on who we are as a company, Simsoft was founded in Stockholm in 1989, and we are the operator division of CLX Communications. We provide and deliver software and services to over 75 MNOs and MVNOs worldwide. And besides fraud and security, we also specialize in mobile core network, charging policy, billing, and CRM solutions. Simsoft also has a host of value-added services offerings for operators. We're very proud to be recognized as a Tier 1 signaling firewall vendor by Rocco, the roaming consulting company, in their 2017 vendor performance report based on perceptions and experiences of 57 MNOs worldwide. Particularly in the area of signaling and security, we contribute to the evolution of the mobile industry by active participation in GSMA working groups and key industry forums. In our 2017 survey, we were proud to see that all of our customers see us as a long-term partner. I would also like to introduce our presenter today. Fredrik is the System and Software Security Advisor at Simsoft and specializes on signaling, IoT, and software security. As part of the CTO office, he assists the product management team and also heads up the Simsoft research program into new vulnerabilities and defensive strategies. He's an experienced product and solution designer who has worked on telecom security and revenue assurance solutions with several vendors and telecom service providers. His main focus since 2010 has been on telecom security and firewalls, both for SMS as well as signaling security. Fredrik has more than 30 years of experience as a programmer and 20 years of experience in reverse engineering. He's twice listed in the GSMA Mobile Security Research Hall of Fame and has submitted accepted pieces of research to the GSMA CVD program. Our webinar today is being recorded and will be available online later on our website, so please do share it with anyone who may be interested but was unable to attend today. If you have any questions during our webinar, please use the question box available, and Fredrik will try to answer as many of them as possible at the end. So Fredrik, we're eager to hear what you have to say.
Okay, so my name is Fredrik Söderlund, and I'll be presenting this, handling this presentation today. First, I'd like to walk you through the agenda of this talk. We'll first have a look at SS7, vulnerable by design, where we'll have a walk through the acknowledged signaling vulnerabilities that we've been looking at for the last couple of years. We'll examine the root of those problems and also look a little bit at the mitigation or the signaling band-aid that is being applied using signaling firewalls. We'll then move into the new class of SS7 vulnerabilities. We'll have a look at malformed packets. We'll look at prerequisites for launching this new type of attack, also looking at attacking and tunneling, and then we'll see how we can craft a multi-stage exploit and actually realize this attack as a proof of concept. So first, a look at SS7 as a protocol, vulnerable by design. What do I mean by that? Well, signaling-based attacks are known and have been known for a long time. Nation states most likely have been using them for more than a decade, and work on mitigating them only really started in a serious way in 2015. However, these attacks are not so much attacks on the protocol in a traditional sense as they are exploiting the expected functionality offered by SS7 networks. So if we look at, for example, location tracking, this can be done using anytime interrogation or provide subscriber info, which are typical map operations in SS7. These can be used to track subscribers or VIPs by reading user profiles, essentially. We also see attacks with regards to profile manipulation, where the attacker is using insert subscriber data or register SS for fraud, call redirection, or even denial of service, and this is done by writing to the user profile, again using the perfectly normal functionality of the network. We also have a third category, which would be subscriber hijacking or denial of service, where the attacker is using, for example, update location to move the targeted subscriber into a VLR under attacker control, and then eavesdropping, for example, on two-factor authentication. Or you can actually also, instead of moving or changing the location of the subscriber, you can in fact erase the subscriber using delete subscriber data to sort of create a denial of service attack. The reason these attacks actually work is that SS7 has a fundamental flaw built into it, which it shares with Diameter. It lacks authentication of the signaling origin source. And this is a fundamental component when communicating over networks. Authentication is required, but when SS7 was built, it was built on trust. These days, we see that trust has been broken. Essentially, the network is much more open. We have much more people with access to the interconnect and SSP providers. So the trust model was essentially never a proper way of protecting the network, and we realize this now and see the consequences. If we had authentication, if we were able to know who was reading a profile, we could prevent it. If we know who is attempting to write to a profile, we can protect it. And if we know who's asking for a location update, we can actually prevent that as well. But on a network like SS7, where everyone is a trusted peer, there is really no barrier against abuse of functionality. And this is what we mean by traditional SS7 attacks or signaling attacks. The industry has responded, and the vendor community has developed signaling firewalls that mitigate this, where we have essentially three different categories of filtering. You have category 1, where you filter the international links for a certain number of operations that should never occur over international links. We then have also category 2, where we filter another set of operations which should never occur against HomeNet subscribers from an outside entity. And this category also covers protection of inbound roamers to some extent, where only the home network of the inbound roamer is allowed to contact them. The third category, category 3, would then be location-based tracking, where the firewall keeps track of where the subscriber is and makes sure that the subscriber cannot start originating traffic from a location where he in fact is not. This also covers location update, where the subscriber is not allowed to make location updates which do not fit into, let's see, the limitations of the physical world. You cannot have a location update in Japan 1 second and then another one in Denmark 2 minutes later. So essentially, these different types of filtering, together with home routing and some whitelisting policies, creates a signaling band-aid, which is a fairly strong protection against these traditional attacks. If we look at signaling-based attacks, we can visualize it as follows. The attacker on the upper left side of the screen is bright red. The attacker takes advantage of this fact that the network on the right, the smiley face on the upper right side of the screen, is obliged to trust any request that it sends toward it. This is an inherent property of the vanilla SS7 network, and the attacker simply asks for sensitive information, and the network happily obliges by providing this information. So information is gained by the attacker, or perhaps a profile may be modified, but the attacker still remains an outsider and is subject to, for example, blacklisting, the filter categories that I mentioned, and can be denied from querying the network further. So signaling, we have a fairly good understanding of how to mitigate signaling threats. On the lower half of the screen, we have instead an attack using malformed packets. Here, the attacker does not merely request information. The attacker is sending a specifically crafted packet containing the exact information required to crash the network node in a predictable way. This crash triggers an infection, and the attacker effectively takes over the network nodes completely. This means that the attacker now, as you can see, the network node on the lower right has turned red. It has become an extension of the attacker, and the attacker has now remote control of this network element. Once this network node has been compromised, the attacker can proceed to scan the local network. The local network has little or no reason not to trust this infected peer, and in fact continues to trust it as if it was behaving normally. But behind the scene, the attacker now has some interesting new capabilities. In the signaling layers that exist on the upper part of the stack, there are some types of attacks that are possible. On the lower side, of course, the attacker now on the bottom has access to different parts of the protocol. Instead of being having to route his attacks, he can actually perform attacks on the lower layers of the stack, even down to the IP layer, so IP, SCTP, and M3UA. So the attacker gains some really interesting capabilities by becoming a local entity on the network. So looking at these malformed packets that are that can be used to create such an attack. Well, when we talk about signaling-based attacks, it's quite clear what the objective is. It's to communicate with the SS7 network in the intended way and to get information or supply new information to affect one or multiple subscribers. When using malformed packets, the attacker has a different objective and it's a little less obvious. The attacker on the left, represented by a person, is looking to exercise some degree of control over the network element on the right. And this control usually falls into one of two categories. Denial of service is one type of control. It aims to disrupt the network element, attacking either the application or the underlying framework or the entire operating system of the receiving node. This behavior can be achieved either through crashing the application or the operating system, or by making the software go into an infinite or near infinite loop. And this can occur sometimes when introducing malformed data in a structured way. The second degree of control is remote code execution, which is more insidious. This requires intimate knowledge of the targeted network element, and the attacker must craft a structured attack packet that transfers control from the application to a malicious payload contained in the attack itself. This type of transfer can be obtained, for example, through a buffer overflow, and this type of attack usually is a little bit more difficult to realize. So looking at malformed packets themselves, how do they actually work? We can compare them in a sense to a letter. So if we look at the malformed packet here on the left, the normal packet, the normal packet on the left, not the malformed. We see that we can compare it to a letter in the sense that it arrives at the country border. It gets sorted according to zip code and delivered to the appropriate city. It is then sent to the post office that governs this particular street. And at that post office, the mailman that covers that street will take the letter and deliver it to the person for which it's intended. In the case of a malformed packet here on the right, the flow is similar in the beginning, but then takes a different turn. The letter still arrives at the country border, is sorted according to zip code and sent to the right city, delivered to the appropriate post office and handed to the mailman. But when the mailman goes to deliver the packet, the letter, he actually delivers it at the border again, repeating the process. And this loop repeats until the entire post office resources are depleted and expire. And this, of course, disrupts the mail service for this region. Another example of a malformed packet would be seen on the left here. The letter would still arrive at the country border, get sorted according to zip code, and delivered at the right street. But the mailman will not deliver it to the person. Instead, it will point out into nowhere or a region which cannot be managed. And the mailman will eventually get lost and service will be disrupted again. This is a different way, which could be done using, let's say, broken relative pointers or things like this in a sense of a malformed data perspective. The third example, of course, is the worst kind. This would be remote code execution. Here, the letter again arrives at the country border, is sorted and sent to the right city. It's delivered to the post office governing the street of the person it should be arriving for. But instead of our friendly mailman, an evil mailman picks up this packet or this letter. He goes to the house of the person, but he doesn't deliver the letter. Instead, he installs a backdoor, performs cleanup, and then delivers the letter to the person. So in the perspective of the person, he received his letter, he is happy. The post office has no reason to suspect anything going wrong because the customers are happy. But in the background, this backdoor has been installed, and the attacker now has complete access to the house of this person and can do essentially whatever he wants. So from our perspective, our goal was to create a proof of concept of remote code execution over SS7. So we wanted to infect a vulnerable network element. We wanted to deploy a command and control server over SS7, and then exercise remote control of this compromised element. And we'll now have a look at the prerequisites on how we achieve this. Because there are a set of prerequisites that have to be fulfilled for us to be able to realize this. The target node has to have a vulnerability. And this vulnerability ideally resides in the application layer, because that allows us to create a routable attack. So this vulnerability should be in the TCAP or GSM map or CAP part of the packet. This part of the network stack is encoded in a format known as ASN1, which is a very old standard built to conserve space, and it's known for complexity and many annoying quirks. For example, it has 3 ways of encoding the length of a parameter. And many of these implementations are broken here and there. The second prerequisite is that the attacker would like to place a known piece of user equipment registered in the target network. This serves the purpose of legitimizing any traffic towards the target network. If all traffic is targeting a real physical device that the network knows, there is never a reason to question why this traffic is being sent. Hence, the UE effectively serves as an alibi for the attacker. Last but not least, the attacker needs to be able to deliver a packet large enough to hold both the exploit and the code for the initial virus installation mechanism, because this is in fact a virus in a sense, or an implant, depending on who you ask. Currently, the size is less than 500 bytes of this initial infection. It's 413 bytes that represent the initial infection, and then 72 bytes, which is the stack used to bypass memory protection and transfer control to the virus body. So, can we fulfill these requirements? First, have a look at, does it exist, a vulnerable ASM1 parser? Well, the common vulnerabilities and exposure list is a publicly known database of vulnerabilities. And these entries are made public. They are essentially ordered by year and discovery time. And it's a common repository for cybersecurity vulnerabilities that is used very often when discussing cybersecurity. Searching this list, of course, gives us well, over 100, in fact, ASM1 vulnerabilities, but not all of these are applicable. But signs point to yes, we can find vulnerable ASM1 parsers, and in fact, many network element vendors use proprietary ASM1 parsers and encoders, and the vulnerabilities in those will not be disclosed to the CVE list. It's even more likely that they will never be discovered by the vendor, because in many cases there is a lack of proper testing and security evaluation in production. The second prerequisite is to be able to register a handset in the target network. We essentially just need to transport the phone to the country and register with the target network as an inbound roamer, and then we have fulfilled this requirement. So what about the last one? Well, sending a 500 byte payload over SS7. It sounds easy, and actually it's not as complicated, but it still requires a bit of examination. There are 2 types of SS7 to consider here. You have M3UA over IP, which is generally quite forgiving with regards to size, and there is no problem sending 500 bytes or more in a single packet. When it comes to TDM over E1, it's a different animal, and it does introduce a hard cap of 272 bytes. So this seems to sort of limit what we can do. The same limitation could in fact be seen also over M2PA over IP. But luckily, there is an intermediate network layer, SCCP, which offers a solution for this. Above 272 bytes, the regular unit data in SCCP is exchanged for extended unit data. And extended unit data offers SCCP fragmentation. It also offers a hop counter, but the fragmentation is what we're looking for. This means that the malicious payload that we're sending, or the attacker is sending, will be fragmented and sent over multiple MTP3 frames. But then, on arrival, it will be reassembled by the SCCP and delivered as a complete large packet to the application. So we'll have our exploit and compromise delivered for us in multiple parts, but then sent to the application as a whole. Fragmentation is nothing strange. It does occur naturally in a SS7 network, and it can happen, for example, with send authentication info responses, where you have multiple quintuplets. Such packets can exceed the size limit, for example. So there's nothing strange about XUDT. It's just much more rare than the UDT, the unit data. So what we see is that all the prerequisites do exist. These attacks can be realized on existing infrastructure. And we also see, since the attacks occur on TCAP and above, that these are routable over the interconnect. So how would we go about this, launching this kind of attack? We'll look at both the attacking and tunneling part in this section. When it comes to crafting the attack, there are some size constraints to consider. But as long as the initial infection can be delivered, we can deliver the rest of the executable code incrementally over a series of packets. So the initial infection is essentially an optimized hook procedure or a filter inside the network interpretation code, or it can be in the network library as well. The secondary infection is the actual command and control server, and this one is delivered in a series of chunks. Since it's delivered in multiple packets, there is really no limit on how big or how evolved it can be. It can be very complex. So it works a bit like this. The initial hook procedure filters all incoming traffic. And if it detects incoming packets holding chunks of the command and control server, it will then absorb those and rebuild the command and control server in memory. The hook must also track possible resends and ensure that all parts are being delivered, because many SS7 deployments are done in high availability and load share. So there is not always a guarantee that the same node will receive all of these chunks sequentially. So the attacker needs to sort of monitor that. It can easily be managed by a simple bit mask. So there are optimized ways of doing that, but it has to be done. Once all the chunks have been delivered, the initial hook will replace itself with a full command and control server, and then the compromised network node will be ready to serve the attacker. To launch the attack and install this initial infection, we need a suitable delivery vehicle. The map reset command is a very good candidate. Reset is nice in the sense that it's perfectly spoofable. We don't need to care about the return. And since we have our user equipment registered in the network, we have an alibi to send this message as if our HLR had been reset. So we will be able to send this message towards the target network without the network questioning why. Reset also has another nice feature. It has a variable size HLR list of IMSIs as an optional parameter. And this list can contain many entries. An IMSI in ASM1 representation is at least 10 bytes in size. You have 8 bytes for the TBCD digits, and then you have a few bytes for the tag and length. So this means that implementations must expect reset to be possibly quite sizable and potentially fragmented. The exploit is triggered by the malform data in the reset packet somewhere, and then the code for the initial infection is actually stored in the optional HLR list. So let's have a look at the call flow. The first stage is the exploit, which is delivered, as I mentioned, in the reset packet. This message is never actually processed by the receiving MSC, but instead it crashes it in a predictable way, installs the hook filter, and then this hook can be installed in any suitable place in the application network traffic handler or in the receive function of libc itself. It all depends on the implementation and what is more practical for the attacker. The hook procedure then stays resident and filters all incoming traffic, and it does this to detect packets that contain subsequent parts of the attack. So these subsequent part of the attacks, the command and control server, are then sent incrementally in empty forward SM. So you have code chunk number 1 being sent first, and then absorbed into the command and control server. Then you have chunk number 2, and in our example, we have 15 chunks covering some 2,000 bytes of proof of concept code. One nice feature is that we can actually target our user equipment that we planted as an alibi, and these empty forward SM will make perfect sense for the target network. So there's no reason to question them either. Once all of these chunks have been sent, the command and control server is assembled, and the attacker can proceed to send commands to this command and control server. And this command and control server then acts as an extension of the attacker inside the compromised network. So this is where the network actually becomes an extension of the attacker. If the attacker would like, he can also send additional code chunks to the server and add functionality. He can do privilege escalation or build out the function set, essentially. The commands are tunneled to the command and control server using empty SMS, and the server responds to the attacker using MO SMS to report back or exfiltrate data. But we also wanted to look a little bit at alternative methods to hopefully increase stealth and potentially evade SS7 firewalls. So is that a way of doing that? Well, looking at something called private extension list, which is a feature of the GSM map protocol, they offer vendors a way of transporting proprietary data over SS7. It does, however, also offer the attacker the ability to transport malformed proprietary data or tunnel information over connection, hiding under the banner of vendor-specific data. So this private extension attack may actually provide better stealth options since it doesn't generate CDRs. But of course, there are advantages of both this method and also the SMS method that we presented before. So let's have a look at them side by side. If we compare these two options, we can see that they all have their pros and cons. SMS provides easy tunneling, simple encoding, and information exchange. We can also have the luxury of controlling the compromised SS7 node using simple SMS. We don't have to have SS7 connectivity for that, which is quite nice and handy. We can actually do everything except the primary infection with a simple phone. On the negative side, SMS generally are logged in CDRs. And even though an attacker with elevated privilege can wipe those CDRs or prevent them from ever being generated, there is always a risk that they are sort of shipped off to a data warehouse before the attacker has a chance to intervene and do his cleanup. The private extension has their upsides and downsides as well. They do provide better stealth. You could also envision doing like a gimmicky attack of vendor-specific targeting there if the proprietary parser is broken and vulnerable. Private extension lists also have the ability to potentially pass through firewall, especially naive firewall, because there is no way a firewall could be sure to understand private extensions, especially if it's a non-allocated ID, because then we flag as unknown. And potentially the firewall then would have to create a false positive. On the negative side, the encoding and the communication protocol is more complex with the private extensions. You need to trigger expected traffic, for example, using update locations. You can trigger insert subscriber data streams, and there you can sort of issue your commands, etc. So you have to communicate slightly differently than with SMS. So SMS is much more practical. Private extensions are also likely to provide lower bandwidth than SMS. On SMS, you have some 130 bytes to work with, which is, in itself is fairly low bandwidth, but on extensions, you should probably calculate that you have less to work with. So now I'll go through a demo of the attack and show you what we've done with this. So I'll first give you an overview of what we're looking at here. On the left side of the screen, we have Wireshark running, and this will show us the traffic being exchanged. And you'll only see the attack and the communication between the target and the attacker. We don't have any noise traffic, natural traffic occurring, and we don't have the SRIs, etc. No, there is no noise. Only the relevant packets are being shown. On the top right of the screen, we have the virtual machine of the attacker. It's running on an ESXi host, running CentOS 7. And on the lower part of the screen, we have the target MSC, which is a simulated vulnerable MSC. It's running on a VirtualBox. So let's proceed with this demo. The infection is launched, targeting is done by GT, essentially. And now we'll start the vulnerable MSC. And then we'll fire away our attack. Targeting, as I mentioned, is done by GT. So first it will establish the M3 link, and then we'll send the two-stage infection. So we see here that the payload stage 1 has been sent. This is the reset command, which is malformed. Even Wireshark reported it. And then the first initial filter is now installed. And every MT forward SM is being filtered according to the IMSI of the destination. And every MT forward SM contains a chunk of code for the command and control server. And once all 15 SMS have been delivered, the command and control server is then installed instead of the primary hook. So this means that the SS7 shell has started. So we now have control, remote control over the compromised network element. So the first stage is in the reset command. And now we'll illustrate how we can actually execute a command. So the attacker will now send the command remotely over this SS7 shell and start the Vim editor on the target machine. And it works. And we can see here that the command was sent in the TPDU of the SMS. And then the command and control server reports back by echoing the command that the command has been executed. And we'll now relaunch the vulnerable MSC and illustrate another command, which essentially shows a built-in command to sort of just crash the element. What we'll do now is to issue a kill command, which essentially elevates privilege and then crashes the vulnerable MSC below. And this, as we can see, it resets and restarts. The last conceptual attack that we'll be showing is the creation of virtual subscribers, which is essentially when the attacker would invent inbound roamers and then use those, for example, to create other sessions. And here we send the vsub command to the command and control server, which is responded to by the command and control server by issuing a stream of update locations. These update locations then will be responded to by the attacker using insert subscriber data, where the attacker can send new commands or provide information for these user profiles. So that's essentially the demo of the attack. We can speak a little bit about mitigation as well. There are, of course, ways of mitigating many of these threats. And these threats, the threats that are associated with malformed packets are best mitigated by looking at the different aspects of these malformed packets. However, there are also methods that an attacker may benefit from knowing how we mitigate these threats. So that will allow the attacker to sort of circumvent some of them. It's very much a classical game of cat and mouse. And as this is a public webinar, we have opted not to hand out mitigation technology publicly at this time. What I can mention is that we have developed a series of defensive techniques and incorporated them in our firewalling functionality. And we feel that we mitigate these threats fairly efficiently. If you're interested in having a discussion regarding this, we offer you to send your details for a one-to-one conf call, and then we can discuss this privately or even under NDA. So now I invite you to ask questions if you have any.
Yeah, thank you very much, Fredrik. Very, very interesting. So yeah, as Fredrik mentioned, we will now be taking questions, and please remember you still have a chance to use the question box in your screens to send them through. And if there is anything not answered today or anything you are still questioning, you can send us an email. So Fredrik, our first question, what do you mean by the attacker becomes an extension of the mentioned MNO? Could you please explain this a bit further?
Well, what happens is that the attacker actually gets remote control of the MSC. And as such, he can execute any commands he likes. He can start scanning the network. This means that other nodes can be further compromised. But the first attack, when you compromise the MSC, the attacker becomes that MSC and controls it remotely. That's what I mean. Okay,
thank you. And another question is whether you've tried this attack on a live node. Is that something that you've done?
Yes.
Yeah.
That's a simple answer. We've tested these. Well, we haven't tested them over interconnect because that would be very dangerous in case the intermediate carriers would be doing some filtering or examination of these packets. We've done testbed examinations of this.
Okay. And is there any information you can disclose about which vendor you tested it on? This is also another question coming through.
Well, no, we can't disclose that. We have tested on vendors, different vendors, and there are multiple vulnerable vendors. But we made our disclosure through the GSMA coordinated disclosure program, and through that we've submitted relevant information and also information to vendors on how to sort of examine their software and to potentially create take hardening measures and test the vulnerabilities themselves.
Okay. Another question coming through is whether is the demo are the demo hacking tools available in any sort of open source sites?
No, they are not. We have decided to keep this closed because they can be quite easily abused.
So yeah, the tools basically they're not available on open source.
No, they're not.
No, that's at least promising to hear. Have you let's see here. Did you use a commercial stack in the vulnerable MSC?
No, in this vulnerable MSC simulation, we did not use commercial stack. We used a very basic implementation just to illustrate the concept of the tunneling and the exploit delivery.
Okay. And the XUDT messages, are they commonly routed?
Well, they usually exist in a very low percentage, and the difference between, let's say, a fraction of a percent to a few percent in some networks. So they exist, but it's good to know that they are a very, very small percentage usually. I think there might be networks that don't have them, but they should occur naturally because they can.
Okay. Are there any real-world implications for our? What are the real-world implications for our subscribers, and what risk does the end subscriber face essentially?
The problem with this type of attack is there is really no limit to the possibilities. Once the attacker has compromised an MSC, he is essentially a trusted peer on the SS7 network inside the network, and can issue queries to the HLR and be perfectly trusted, and also proceed to hack other elements. And these, as you have, as an attacker, have a very different degree of, how shall I say, reach when you are a local peer. This means that you can actually attack on the IP layer and the SCP layer and the M3UA layer. So you're both trusted and you're also on the local network. This expands your possibilities greatly. And if you compromise more than one node, you of course get even more reach into the network. So you can essentially, if you compromise an HLR from this MSC, for example, you can read any user data there. You can also eavesdrop on subscribers because you can see all the signaling traffic they generate. So if you have a specific target in mind and you compromise an MSC or multiple MSCs in a network where this subscriber is, you can of course track the subscriber or intercept data or whatever you want.
Okay. You did mention that you did not test over interconnect. Would it matter if we use MTP, M3UA, or M2PA?
Well, M3UA is, like I mentioned at the beginning, is fairly forgiving in terms of size. MTP3 and M2PA is where the fragmentation would occur. So that's the main difference, I would say. But many times you'll see that if you send something over the interconnect, it may actually pass through TDM links at some point.
Okay. Here's an interesting question. Is there some solution to test the robustness of the network stack to detect this kind of issue before going to production?
Yes, I mean that's what fuzzing is all about. Sending malformed data into a parser and seeing if it's robust or not. You will be looking for things like type length value verification, checking that there are no out of bounds pointers, or that packets adhere to the size, or that there are no negative pointers and things like that. There's a lot of stuff you can do, but fuzzing is essentially that, testing the robustness of the code that interprets the network traffic.
Okay. here's perhaps another question that's quite interesting. How is it possible that diameter is as vulnerable as SS7?
Because it was designed in a similar way and even more poorly in some respects. This type of attack has actually been realized on diameter as well. We've seen reports on remote code execution on diameter. I think P1 Security, for example, presented this a few years ago. It's yeah, diameter is in some respects worse than SS7, in fact, because it offers should I say, transparent spoofing. The attacker actually gets the response when they impersonate someone. The attacker doesn't have that luxury on SS7.
Okay. So SMS messages, they generate CDRs. Here's a question: whether you've tested on other messages for CNC that do not generate CDRs.
We are exploring this further, of course, and we might make an update on other type of attack packets. But we've decided to stay with these, the reset packet for now, because we don't want to sort of. We wanted to show this conceptually first. There are other ways of attacking. As I mentioned, you can use insert subscriber data. That would be something that you would then trigger. So you would have the initial infection generate, for example, update locations, and then the attacker would use insert subscriber data with these extension containers, for example, to carry command and control server components. This is something that's one example, but there are other ways as well. There are some strange SS7 packets that you can use, and you can also potentially store things in parameters that aren't used depending on the implementations of the network nodes that you're attacking. So it's there's plenty to play around with, but at this point we're presenting just this part of it, but we're looking more into this as well.
Okay. You mentioned about virtualized MSE. Is it something that we need to look out for? Is it a design flaw?
No. I mean that's no, and that's a good question because it has nothing to do with the virtualization at all. This is something that happens on the application layer of the stack, and it's a generic thing, really. It's it doesn't have to do with anything like the physical or virtual platform that it runs on.
Okay, so this type of attack exploits a vulnerability in the SS7 stack, or is it the application residing on the server? Is that
the vulnerability would be specific to the application that resides on the machine, on the MSE application. It exploits the way that SS7 works and the fragmentation that it allows, but the design flaw is in the MSE, and that's where it should be fixed, or in some ways mitigated in firewalling.
all right? We have a few more questions coming in here. Is ASN1 parser vulnerabilities the only ones that could let me see that could this type of attack relies on?
Not really. It's I mean, the SCCP also offers some parts that you could potentially use to crash something, but it's in my experience much easier to do it on the ASN1 part. But you could potentially route a packet with a broken SCCP structure as well. But it's a higher risk for the attacker, and I would probably say that it's not as a good idea to do. That of course changes dramatically if you have one compromised node and you become a local entity on the network. Then all bets are off, and you can just route by point code or attack over IP, and then you have access to the full stack. So that's it depends on the perspective of the attacker, and that's also why I highlighted the fact that the attacker gains a different degree of capability once he has compromised one MSC.
Okay, lots of good questions here. What happens on the MSC MSS VLR if it receives the malformed packet? Can you explain a bit more in detail if possible?
Yeah, sure. What happens is that a part of the packet that's being delivered contains a snippet of code, essentially, which then installs this filter. The first thing that happens is the exploit itself, which can be a buffer overflow. That means that the return address from a procedure is overwritten. When the address is overwritten, it redirects the flow of execution to a different place. In the case of our example, it actually redirects it into a part of libc, which can be statically linked into an application, for example. I don't know how much time we have to spend. I could.
Yeah, we have actually a lot of questions that have come in, so I've tried to pick out a few of them, but I think
I'll just run through briefly. Okay, so what happens is that the return address is overwritten by an address into libc, which is a misaligned instruction. It's a pop R15, for example, which is a non-volatile register. Instead of returning to that address, we return to that address +1, skipping the 41 prefix of the instruction, and then turns that into a pop RDI, which populates the first parameter for the mprotect call. Then we do the same thing for R14 in the instruction. So we return to different addresses into libc using return-oriented programming, eventually returning to mprotect, which deprotects the stack, and this is where we execute our code that then installs the command, the initial infection. So we allocated a portion of memory, install our hook procedure, and then patch the receive function of the vulnerable MSC, redirects that receive function into the hook procedure, and from there we filter all incoming traffic, determine if it's an M2UA packet or an M2Q packet, and then we have a look at it, look inside, and see if we have the correct IMSI, which is the target equipment that signifies that a code chunk is being delivered. This code chunk is then stored, and once every code chunk has been delivered to this initial infection, we replace the initial hook with the secondary hook, which is the command and control server. So that's probably the shortest way of explaining it. The person who asked the question is welcome to contact me, and we can have a walkthrough, and I can probably show you, trace you through the attack in IDA or something like that.
Sounds good, perfect. So a question about the firewall. Does the firewall analyze the patterns of the bits for the vulnerabilities?
Not for the vulnerabilities, but it does have some capability of looking at potential attacks and the delivery vehicles of attacks. So it doesn't look at the vulnerability. The vulnerability resides in the MSC. The actual attack resides in the malform pack.
Great. A question about whether the test was done on a network with C1, C4 filtering in place.
No, it was not.
It was not, all right. Perhaps a general question. Are there any other network attacks that you've not mentioned here today that you care to disclose?
Other networks attack in what perspective?
I'm assuming the person is asking if there's other types of attacks other than the ones that you've gone through today.
No. No, I don't think so. I mean, it's no. This talk is basically on this topic, and other attacks that we're researching is subject to different presentations later, I would say.
Okay, and I will ask one last question because we won't have time to run through them all. But could you please elaborate a bit more on the volatility of diameter over SS7? We know diameter is 7 times larger than SS7. So why is diameter in a sense worse than SS7?
7 times larger in what sense? That is well, that's Well, diameter is a bit of a strange animal because it has 24 bits defining the size of each parameter. So essentially, you can make packets fairly large. You can make them 16 megabytes or so. So that's you have plenty of space to work with. The underlying protocols will let you deliver large chunks before they are passed to the application. You have the possibility of spoofing with response. Of course, that's bad in diameter. I think that diameter is broken in some respects, and I would say it's vulnerable, but it has less operations in use today. I mean, there is no reliable way of retrieving an IMSI over diameter today that I know of. There are interfaces that exist on paper, but they're not deployed anywhere, into my knowledge. So diameter attacks would still have to rely on some type of previous knowledge or understanding of who we are attacking and which IMSI you are targeting, etc.
Okay, I think that's all the questions we have time for today. There are still lots of questions here that we haven't had time to answer. So please do send them in an email to us. I'd like to thank you, Fredrik, and all of you for joining today's webinar. I think it's really important for our industry that this sort of information sharing takes place and that we're all aware of the new threats around network security. So I hope you all leave this webinar a little wiser. And like I said, if you have any other questions, please do send them to us. So thank you all and enjoy the rest of your day.